This chapter deals with the general theory of relativity. All right, so first of all, the last chapter where we studied special relativity, we were talking about objects that were moving at constant velocity. General theory of relativity deals with situations where you have an accelerated frame of reference rather than a frame of reference moving just at constant velocity. All right, now the first step in understanding general relativity is what's called the equivalence principle. So the equivalence principle simply means that when an object is in an accelerated frame of reference, so we take a look at this little picture here, it looks like Einstein, and he's in a situation where it's an elevator, part of a spaceship if you want. It is accelerating here upward at a speed of, at a rate of 9.8 meters per second squared. So he's in deep space, and he's in this rocket ship, and the rocket ship is accelerating upward at that rate, the same acceleration due to gravity that we know to be on Earth. Okay, over here we have Newton, and Newton is just sitting there at rest on Earth, and he's looking there and he sees the apple. Okay, so the equivalence principle simply says that this situation where you're accelerating in the rocket ship in deep space upward at a rate of 9.8 meters per second squared is exactly equivalent to this situation when you're on Earth and you're in this gravitational field that accelerates the object at 9.8 meters per second squared. So we can see you've got the apple falling here, like the old story with Newton, and Einstein would see that exact same rate, that apple would fall at the same rate. He would feel the pressure of the bottom of the elevator on his feet, just like, although we don't necessarily think of it, but Newton would feel the same way on Earth, feeling the pressure of the Earth beneath his feet. The first consequence of the equivalence principle is the bending of light by gravity. So let's take a look at the spaceship over here, and let's pretend that this little object here is a beam of light. And if you were an outside observer and you could, this walls of the spaceship here were transparent, the spaceship takes off. From your point of view, you'd see this beam of light go straight across like so. However, if you're inside the spaceship, then what's going to happen is the beam of light comes in here, and because the spaceship is accelerating upward, the beam of light appears from the inside to be bending. In other words, it's going to travel a small distance at the halfway point, but it's going to travel a much bigger distance vertically when it gets to this point, because the spaceship is accelerating and it's going faster. So from within the spaceship, you tend to see the bending of this beam of light. Now, by the equivalence principle, that says that this is equivalent to being in a gravitational field, so therefore we conclude that a gravitational field has the ability to bend light. And as you'll see in your text, there is some, Einstein actually made some predictions about this, and these predictions have been confirmed. We saw time dilation with special relativity. Well, it turns out that time dilation also shows up in general relativity, and it's affected by a gravitational field. Now, to try to get a little bit of understanding of that, let's take a look at this disk here, which is spinning, and we have 3 clocks, 1, 2, and 3. Clock 3 here is at rest relative to this accelerating frame of reference, so it is going to show the proper time. Clock 1, on the other hand, clock 1 is directly in the center here, and so therefore it is not moving. So therefore the time shown by clock 1 and by clock 3 are going to be the same. They're going to run at the same rate. Clock 2, however, is clearly in motion. And because it's in motion from special relativity, we know that it's going to run slower. Time is going to run slower. Furthermore, it's accelerating since it's spinning around here. This is centripetal acceleration, and you might recall that from a few chapters ago. We studied that. You can go back and refresh your memory on it if you don't remember it. But in any event, as clock 1 begins to approach the position of clock 2, it's going to move faster, and it's also its rate of acceleration is going to increase as it moves outward. So by the equivalence principle, therefore that means that since the clock runs slower as it approaches a greater and greater acceleration by the equivalence principle, that means that in a gravitational field, clocks are going to run slower, and as the gravitational field increases, the time dilation gets larger. The other thing that special relativity predicted was this issue of length contraction. So we're going to use exactly the same argument as we used in the previous slide. This ruler right here is moving around in a circular path. Since it's in motion, it's going to experience a certain amount of length contraction. Furthermore, this ruler over here, if it was to be shrunk down to a point, is not in motion. But as it moves in this direction, then the length contraction is going to be greater and greater and greater and greater. Now the length contraction only applies to the direction parallel to this ruler. It doesn't apply to this direction here that's perpendicular to the ruler. So when you apply the equivalence principle, that means that there's going to be a length contraction due to a gravitational field in certain dimensions. And what that does is, in effect, it creates a new kind of geometry. It's not going to be like plane geometry where, for example, circumference is equal to pi times diameter. It's going to be something somewhat different. Now, this only applies to extremely strong, where it's noticeable, this only applies to extremely strong gravitational fields. In ordinary gravitational fields like we have here on Earth, the effect is negligible. But much stronger fields, this warping of space-time, as it's called, because it's not just the 3 dimensions, it also includes time, is going to be significant in large gravitational fields. And there's a little, if you don't quite understand how you can warp space-time, or can't visualize that in your mind, Einstein couldn't either. And there's actually a little bit of a quote in the book here that what he says about that. But it does exist, and again, it's one of these things that have been experimentally measured. And in the next slide, you'll see sort of a picture of what it might look like. So here's a picture that shows the Earth right here, and around it, this is sort of just a depiction of space-time. Notice how it is warped here around the Earth due to the gravitational field of the Earth. This apparently is just a satellite here. I took the image off the web, but I was very impressed on this picture here. Newton's laws are still used and are very valid in calculating the orbits of planets, satellites such as this, and it's still an extremely useful tool. However, in very strong gravitational fields, it tends to break down. So when physicists are predicting the behavior of objects near a black hole, for instance, they have to apply general relativity rather than Newton's laws to get an accurate description of what's going on. So there's obviously, this is just a very superficial treatment of general relativity. It gets to be extremely mathematical, but there's a lot more reading out there that you can do if you're interested in this topic. It truly is fascinating. And this is our last lecture, so I hope you've enjoyed the course, and I've had fun doing these little lectures. I hope you're able to bear with me with my gravelly voice, and I wish you all the best, and hopefully you'll maintain an interest in physics forever.